All right, here I'm going to show a solution for an AP Physics styled question. This one is not an official question from the College Board, but it was provided by Bedford, Freeman, and Worth and has been released publicly, so you're welcome to help yourself to the question. In fact, there are 5 questions that they prepared for helping you to prepare for this year's exam. I strongly encourage you to download the PDF via the link in the description below. Try out these questions before you watch my solutions, but hopefully the solutions that I'm about to show you here will be of some help after you've done that. So let's get right into it. This is another example. I just recorded an official AP paragraph style question. So this one is rather similar in that it's also a paragraph length question, but it's distinctly different. So it's a good question. All right, so here's what's going on in this question. It says a student throws a small rubber ball at a brick wall. The ball is thrown, leaving the person's hand at approximately shoulder height at an angle above the horizontal. So immediately you're thinking, hopefully, projectile motion. It's a ball that has just been thrown. Fine. The ball strikes the wall at the moment when its velocity is horizontal. That's an important detail that I think we're going to have to make use of later. So the ball strikes the wall at the moment when its velocity is horizontal. Of course, that tells me that the ball was rising, but of course its velocity will be horizontal only at that moment that it's at the highest point. So if it hadn't hit the brick wall, it would have just continued past that point, but would have been starting to come back down. Again, if the brick wall wasn't there. Now, we're told that the ball bounces off of the wall and strikes the ground some distance from the wall. Okay, so that's a bit vague, but fine. The question part A is kind of a question that I think is going to throw a lot of students. This is something that I don't think is covered very thoroughly, at least very often. That's been my experience in talking to various students and teachers. So this is an important idea in AP Physics. If you have not come across this before, I strongly encourage you to try to understand it from this video, if nothing else. Okay, so part A is saying, is the object model appropriate for analyzing the motion of the ball for the entire time from when it leaves the thrower's hand until it strikes the ground? Briefly justify your answer. Okay, so let me just explain what is meant by the object model. In AP Physics especially, we tend to focus on 2 different models that we can use for considering real-world objects. So the first is the object model. The object model is a simple model. Okay, so let me just be clear here. The object model is as simple as it really possibly can be. There are a number of restrictions for the object model. It assumes, for example, that objects are rigid, that they cannot possibly change their shape, and they also cannot store any form of energy other than kinetic energy. So let me just kind of put that in here. Kinetic energy is the only form of energy available to an object. Now, for the record, there is another model that we can make use of. The alternative is a system model. So the system model extends beyond where the object model leaves off. A system can have multiple objects in it, for one thing. They can interact with each other via forces that we can relate to a form of potential energy, so other forms of energy are available of note. And so systems are just like one step above the object model, just to be clear about that. So part A is asking us, is the object model appropriate for the entire motion, including, from when it was released by the thrower's hand until it strikes the ground? So what I'm thinking here is, if we were only considering the projectile motion, I would say absolutely yes. It doesn't matter if it was a ball or a block or a brick or a bicycle. If you're only considering the projectile motion of it, then it doesn't really matter what it's made out of or, what's going on inside of that object. So projectile motion, the object model is fine. However, this question includes something really critically important that I've already outlined here. Just to double outline it here. It strikes the wall, and of course we know that it bounces back from the wall. So that bounce is actually more complicated than we sometimes like to pretend that it is. When a rubber ball strikes a brick wall, the ball actually changes shape. So assuming it was a sphere before it hit the wall, during the small amount of time that it is actually in contact with the ball gets squished. It deforms into a new shape, And that squishing of the rubber actually stores a new form of energy that we can generalize as an internal energy, or you might want to call it an elastic, potential energy or something like that. But the point that I want to really emphasize here is that that bounce is somewhat complicated. Like, to understand the true physics of what's going on for that brief interval of time that the ball is actually in contact with the wall. Now, in physics, including AP physics, we will sometimes simplify this and say, well, we'll just ignore that and we'll just pretend that the bounce was instantaneous. One moment it was heading towards the wall and magic, the next moment it's going the other way. So we do sometimes simplify it down to that, but being a paragraph length question here and being specifically told that it was a rubber ball, so the material was actually called out here, right? So I think that we're going to have to incorporate all of this into our answers throughout this question. In fact, it's going to be a critical piece of this question. Okay, so being a written form of a question, I've already written up, or typed up rather, my own answer to this. So rather than write up an answer, I'm just going to scroll and reveal it, and we'll just talk about it. So question is the object model appropriate? Here is my answer, which I claim to be an example of a good answer. So my answer is no, okay? And I want to make that clear straight away. I answered the question because it fundamentally is a yes or no question, so no, it's not. Now, of course, it said to briefly justify your answer, so everything that follows is that. So my answer, again, no. And I'm kind of calling out what I just talked about. The only form of energy included in the object model is kinetic energy. So it is applicable only when, there's a typo that I made I didn't catch. Only when it is the only relevant form of energy is what I meant to say there. Okay, so the object model in particular, I want to call out, it ignores changes in internal structure. So that's a limitation of the object model, which is often acceptable. But for the situation we're dealing with, that makes it not applicable. So it cannot account for the internal energy of the ball during the collision. So that's the real issue that I have here, is that collision. In fact, I elaborate by saying, i.e., when it is momentarily not moving. So that's like right at that kind of fundamental moment there of having traveled one way towards the wall and soon to be traveling the other way, but momentarily going neither way. So when it's momentarily not moving but has internal energy resulting from its impact with the wall. Okay, so that's my answer to that. And again, if you haven't come across the concept of object model and system model, I strongly encourage you to look that up if you have the ability to do so in a textbook, or if not, maybe just look it up on the internet. But hopefully my quick summary here will be of considerable help in that. Okay, so that's really it for part A, but let me show you the scoring guideline that was also created for this question. So this question was, it came up to be 9 points. So 2 of those 9 points are found within part A, and I'll show you the way the author of the question allocated those 2 points. Okay, so it was 1 point for stating a feature required to use the object model. So let's see if my answer does include that piece of it. So 1 point for stating a feature required to use the object model. So did I explain in my question what the object model is, and maybe in particular calling out a limitation? And of course, yes, I did. I called out right here that the only form of energy included in the object model is kinetic energy, and so it's applicable only when, etc. Okay, so I'll just kind of stop at that. But yes, I did. I included a description of what the object model is and what features are required in order to use it, meaningfully. There was a second point. Okay, so let's get this up here. Oh, it's not working for some reason. My stylus is acting strange. There we go. Okay, so one additional point for correctly relating the stated feature to the situation we're dealing with here, right? Like the scenario. So how does that pertain? Having talked about the object model is important, but what's the relevance to this scenario? Did I do that in my answer? And yes, I did. So after explaining, I just elaborated on a bit more. I said ignores, and so it cannot account, maybe right around here, cannot account for the internal energy of the ball during the collision. And of course, the rest is just elaborating on that detail. But I would say that, yes, that would earn me that point. And so I would get both of the 2 points that this part of the question is worth. All right, now, By far, the more interesting and challenging part of this question, though, is coming up now in Part B. Now, there are only two parts, so this Part B is the end of the question. Okay, so this question says, in a clear, coherent, paragraph length response. Now, if you haven't watched my previous video that included the paragraph length response, I'd encourage you to go watch that because I talk about paragraph length questions in a more general sense here. I'm not going to repeat all of that information here, although I suspect some of it will inevitably come up. In any case, we have to give a paragraph length response to describe the motion of the ball from the instant it is released. Okay, so we're not worried about how it got thrown. The person's hand, for example, how it interacted with the ball is not being included. So from the instant after it is released until it hits the ground. And when I read until it hits the ground, my interpretation of that is it has arrived at the ground. I mean, like the impact has maybe started, if you will, but the full effect of the impact has not been realized. I don't need to discuss if it's going to then bounce from the ground or sink into the ground and stop. I don't think that's within the scope of this question. So I'm going to only consider up until that moment of like first contact, if you will, with the ground, which is to say it would still be moving quickly. Okay, now, it also says to take your system. Okay, now this is a word that I just mentioned in talking about the object model as compared to the system model. So when we're discussing especially things like energy, it's important to define our system. So that is sometimes our choice, in which case we would just communicate what our choice is. But in this question, it's being specified for us. So take your system to be just the ball. Okay, now, this is going to be another point that I suspect a lot of students are going to be unfamiliar with. So hang on, I really, really need to explain this. And if you're writing the AP Physics exam, this is critical information that I'm going to be explaining right now. Okay, I suspect that a lot of you have come across the equation for potential energy from gravity. I like to write that as the U gravity, but sometimes you might come across it abbreviated as PE for gravity, whatever the case is. It doesn't matter what you label it as. So potential energy from gravity. I usually use UG, but call it whatever you will. The equation that you've probably seen is mgh. Okay, so this is a well-known equation. It gets used fairly often, but there's an important context that is often missing from this. So let me explain. This equation really is all about an interaction of two objects. Even though there's only one m in the equation, don't forget that g itself would be coming from another object, most typically for us, planet Earth. Okay, so this equation is really only makes sense, let's say, in a system that includes, typo there, includes both the object of mass m, which is directly referred to in the equation, and the, I'm just going to assume it's a planet because it most typically would be. So let me just say planet, but I mean, it could be a moon or really it could be anything, but let's just say planet here. And the planet which is ultimately creating the gravitational field G, often referred to as an acceleration due to gravity. But nonetheless, for us, that would be that familiar 9.8 number that is the result of planet Earth, right? We're near the surface of the Earth. Okay, so what does all of this mean for this question? Well, our system is, again, just to stress this, just the ball. So notice that our system does not include Earth. Okay, so I really want to spell this out for us. Let's call this out here. System does not. This is my commentary to you, by the way. I would not be writing this as my answer. In fact, my answer I, again, wrote up or typed up ahead of time. I'll scroll into it right away. So this is just my commentary to you. This is not part of my answer. None of what I've just written here is part of my answer. Okay, so the system does not include Earth. So the very notion of a potential energy is not applicable to what we are about to write about. Just wanted to clarify that. That's why we are going to have to consider the force of gravity, because the reality is there is a force of gravity on our ball, and it is affecting the motion of it, but we're going to have to consider, in fact, let me just say, therefore, The force of gravity is an external force. And external forces absolutely can do work to your system. They can add or remove energy to or from your system. But to be clear, they cannot be included in any notion of a potential energy. Potential energy is really only applicable to these forces, special forces, conservative forces, when they're internal to the system being considered. All right. So just to continue reading the question here before I scroll into my actual answer, be sure to address, and there's a long list here, be sure to address the position, the velocity, the acceleration, the energy of the system. In fact, let's get that in there, the energy of the system, in your description, and justify your description with reasoning based on physics principles. So this is like wide open. And in fact, that's one of the sometimes intimidating features of this paragraph length response. Now, of course, I had the luxury of looking at the point allocation before I wrote up my response. So I'm going to be honest with you in saying that I, in effect, kind of cheated to make sure that I got every point within it. But to be perfectly honest with you, I suspect that if I hadn't done that, if I had just sat down and, as a physics teacher, wrote up my answer, to the point that I would have felt that it was good, good and, in my estimation, complete. To be perfectly honest with you, I probably would have missed at least one of the points that ultimately are going to be found in this allocation. So, in fact, probably I would have got 6 out of 7, because there's one detail I know I probably wouldn't have mentioned. I understand it, of course, I just wouldn't have thought to include it in my answer. So, just all that we can really aim to do here is to be as complete as we possibly can be, including all relevant and correct information here. There's a lot to talk about. So my answer, I'm going to warn you right now, it's rather lengthy, but it really needed to be in order to get all of these, ultimately 7 points that are wrapped up in this question. Okay, so I'm going to reveal my answer now, and we'll talk about it in a minute. In fact, here it is. And again, even though it's a, quote, paragraph, I did choose to, I think it made sense for me to kind of just visually block this into fundamentally, I think, 3 parts. So, okay, let's just look at this first part here. Okay, so the first part of my answer, just kind of here, is this. So when the ball is released, it has kinetic energy. It moves toward the wall in projectile motion. That should be clear. Its horizontal component of velocity, I'm just trying to talk about the velocity because they told me to talk about that, right? So the velocity, its horizontal component of velocity will be constant since there is no net force in that component. So I'm even explaining why it's doing what I'm not just saying the fact that it's moving this way, I'm trying to explain why it's moving that way. So it'll have a constant horizontal component of velocity since there is no net force in that component, but the vertically downward force of gravity causes the ball to accelerate downwards. So its vertical component of velocity decreases until it is 0. Now, how did I know that it would decrease until it was 0? Well, because the question specified that it would be striking the wall at the moment its velocity was momentarily horizontal. So I talk about it striking the wall, at which point the ball is at its maximum height, since that fact, right? The velocity is momentarily horizontal, which is to say it has stopped rising. Okay, so in this block, and again, I'm not done, this is not the entirety of my answer, but in this block I chose to mostly feature on the kinematics. I did mention kinetic energy, but this is mostly talking about the velocity and the acceleration of the object. I didn't really explicitly talk about position. In hindsight, I probably could have, and it certainly wouldn't have hurt anything to include it. Its position changes, along the horizontal, it's rising to a higher position along the vertical. I didn't include that because I thought maybe it was too obvious, and I also had the hindsight of knowing where the points were. So if you had no idea where the points were, it probably would have been reasonable to, at least touch upon the position since it was mentioned in the question. All right, so let me continue with my answer to this next piece. So while moving, in fact, let me just kind of clear this. I'm using highlight just so you can keep track of where I am here. So while moving towards the wall, the force of gravity is external to the system. Okay, so that's what I just talked about. System, the force of gravity from Earth, it's not part of the system, so it's an external force. So I cannot talk about potential energy, but I can talk about work. So strictly speaking, internal forces are incapable of doing work. And again, yet another detail that is frequently missed in the world of AP physics. It wasn't really needed for this question because there are no internal forces, but bear that in mind. I'm sure that'll come up in a future question. So it does negative work, since the ball has an upward component motion, which is opposite the direction of the force of gravity. So negative work is happening, and that's why. Now that reduces the kinetic energy of the ball as it approaches the wall, and then of course there's this complicated impact. So I tried to explain it in as clear a way as I possibly could here, bearing in mind that I'm not ultimately writing a multi-page, treatise on this topic. This was just intended to be a, quote, paragraph, although I think it's a rather long one. Okay, so upon impact with the wall, some of its kinetic energy, I don't know how much, but I'm trying to answer this in a reasonably real-world way here. So probably some of the kinetic energy, right, is quickly transformed into internal energy. So this is that ball, rubber ball, that is kind of squished at that brief interval of time when it's still in contact with the wall. In fact, I talk about that. It's stored in the ball as its shape changes due to the forces that are exerted from the wall. Some of that internal energy is then transformed back into kinetic energy as the ball rebounds from the wall. And then, just to go one step further here, after leaving the ball again has only kinetic energy. Remember that a single object can have only kinetic energy. There's no availability of any form of energy beyond that. So the ball can only have kinetic energy. I actually misspoke. We're not using the object model, but it does have primarily kinetic energy. Certainly no potential energy from gravity. So the impact also dissipated some energy, assuming that the collision was not perfectly elastic. So the ball might have warmed up. That's why I was kind of correcting myself a moment ago. We're not using the object model, so it very well probably does have some thermal energy that I didn't explicitly talk about. The wall probably is a little bit warmer now, the air, some sound, etc. But generally speaking, I just mentioned that dissipation of energy because I thought it was important. Turns out that wouldn't have been needed for the points, but I did include it nonetheless. So then I go into my third part, and of course that second part was largely about energy. The focus there was absolutely on energy. So this final part here, just to wrap things up, as the ball moves away from the wall, I've addressed approaching the wall, I've addressed that brief interval of time that it's in contact with the wall. So let me now talk about that third part of the motion, if you want to think of it that way. So the ball is now moving away from the wall after bouncing from it. So what's happening here is it's much more simple. The ball again moves as a projectile, as described above. I didn't think I had to repeat every detail, although there is a significant difference here, that the force of gravity is now doing positive work because it has a downward component of motion, right? So the force of gravity does positive work, but that is importantly going to cause it to increase the vertical component of velocity. And of course, the magnitude of the ball's vertical component of velocity increases from 0 to its initial value. So this turned out to be really important, and this is probably the part I would have missed. In fact, I'm sure I would have missed it if I hadn't seen the point allocation ahead of time. So, and again, not that I don't understand it, but I probably just wouldn't have thought to include this in my answer. So don't feel terrible if you did try this on your own and you didn't get all 7 points. Don't forget, realistically speaking, your objective need not be to get 100% on this exam. If you're writing the AP Physics exam and getting a good mark, upwards of 75+%, you are highly likely to score a 5, right? And there is no 6. So if in any one year the cutoff ends up being at 75% and you get 76%, congratulations, you walk away with a 5, which is the same end result as the person who got 99%. So don't feel terrible if you miss a point here or there, is what I'm saying, as long as you're scooping up most of them because of your demonstration of a solid understanding of physics. Okay, anyway, just to finish this off here, from 0 to its initial value, when it is momentarily at the same height it was thrown from, that wasn't the key piece, but I thought I'd introduce that to lead into what ended up being a key piece. It increases to even larger magnitudes as it moves to lower heights. So don't forget that it was thrown from, just to reveal this to you, remind you of it. The question told us that it was thrown from, in fact, let me just get rid of this old highlighting. Okay, it was thrown from, where are we at here? It was thrown from approximately shoulder height. So notice that is distinctly above ground level, and ultimately it's going to strike the ground. So An important part of this question, which may or may not be obvious to you, is that it is going to go below its starting point. So even lower than where it began. And of course, the relevance of that is right here. So it will go to even larger magnitudes, just to kind of re-emphasize this, even larger magnitudes as it moves to lower heights. In fact, it'll be at its maximum, I'm talking about the vertical component of its velocity, just when it strikes the ground. So at that initial moment of making contact with the ground, of course, it will then change in some dramatic way that we need not get into right now. Okay, so this is my paragraph length answer. And honestly, as far as even paragraph length answers go, this is admittedly a long one. But I thought it was a really good question because it really is making us think about all of these different facets of the motion of this ball. And that's something that these paragraph length questions are often doing. They're trying to get us to pull multiple ideas together. Now, is there more that we could have talked about? I mean, theoretically, sure. It turns out this is definitely adequate. But to be clear, do not try to really go beyond what you've been asked to do. For example, I could have written a whole other section here talking about the momentum of the ball. I mean, I could have, and I could have included a whole bunch of correct information about how the momentum of the ball is changing, and there's an impulse coming from the force of gravity. I mean, it would have been correct physics had I included that, but that really would not have been a good idea. I would go so far as to say that for the sake of the question that we were asked, and I'll remind you, position, velocity, acceleration, energy, momentum was not on that list. So had I included momentum, there's a potential, again, not knowing the scoring guide ahead of time at least, there could easily have been a potential that talking about irrelevant ideas could have cost me a mark. So just be warned of that. Don't get into irrelevant things. Be complete and be thorough about what you are being asked about. Don't extend into topics beyond that. Okay, so let me actually show you where each of these 7 points came from, and again, we'll try to find them in my answer. Okay, so 1 point, let's just look at one at a time here. So this first point, 1 point is allocated for correctly using Newton's second law in one dimension perpendicular to Earth's surface. Okay, so perpendicular Earth's surface, basically we mean vertical. Okay, and again, you're looking at this scoring guide that was created by the author of this question. So this is not my wording. I'm just trying to add a little bit of clarity to it. Perpendicular Earth's surface, vertical. Either explicitly or implicitly. So to be clear about this, explicitly means you would have had to call it out by name, for example. According to Newton's second law, something's going to happen. I didn't do that in my answer, but fortunately I didn't have to, right? Because I could have done so implicitly. Implicitly just means, okay, I didn't name it, but I'm very much applying the concept here to correctly describe the motion of the vertical direction. So this point is all about the vertical motion, including at least implicitly the concept of Newton's second law. So did I do that? And the answer is, you bet I did. And again, because I had the foresight of knowing where the points were, I made sure I included all of these things. So let me just quickly find it. I think right around here. But the vertical downward force of gravity causes the ball to accelerate downwards. The rest is even yet additional detail here. But you could argue, just from that piece of it, the vertically downward, there is a force of gravity that causes it to accelerate downwards. So implicitly, not explicitly, but implicitly, I have just applied Newton's second law to correctly discuss the vertical motion, right? So I think that would be, that would warrant that point right there. Okay, the next point. 1 point for using Newton's first law, or reasoning in terms of zero net force in one dimension, parallel to Earth's surface. Okay, parallel to Earth's surface, we're now talking about, horizontal. Either explicitly or implicitly, so again, we don't have to call it out by name, to correctly describe the horizontal motion. So have I correctly described horizontal motion, again, utilizing, if not calling out, Newton's laws? And yes, I did. It is where? In fact, I did it in a slightly different order. Of course, that is fine. The exact order is not important here. So its horizontal component of velocity will be constant, since there is no net force in that component. Okay, so you get the idea there. So in that block of text here, you could say that I have exactly satisfied that point, and so earned it. Okay, the next point. Let's see here, we'll go to an orange. 1 point for stating that the ball is at its maximum height when it strikes the wall, since the vertical component of the velocity is 0. So again, you might have missed this, but I did include it in my even in my original thinking before I read where the points were, because I did call that out. Okay, when I was reading the original description of how it moves, that kind of jumped out at me. Oh, actually, didn't scroll enough. Just to remind you of that, analyzing. Okay, oh, right here, it strikes the wall at the moment when its velocity is horizontal. That jumped off the page at me when I read it for the first time, indicating to me that it was at its maximum height that it would have reached even without an impact. Okay, so did I include that in my answer? Yes, of course. Where? At which point the ball... Okay, so at impact, at which point... In fact, let's just kind of get it in here. At which point the ball is at its maximum height since its velocity is momentarily horizontal. Okay, so right kind of in there, between those two square brackets. So I've earned that point. Next point. Let's see, I'll go to a, I guess, highlighter. So 1 point for a correct statement that the kinetic energy of the ball changes as it is in flight due to work done by the force of gravity. So this point doesn't even call out anything in tremendous detail, like the kinetic energy is decreasing and positive work, negative work. Really, this point is just kind of making sure that you're, correctly discussing that concept of the kinetic energy changing as it is affected by the work done by the force of gravity. So, in fact, notice that actually the author of this question, again, this is not me, specifically called out what I had mentioned to you earlier. No credit is going to be given if you discuss this in terms of gravitational potential energy. So, again, everything to do with the choice of how the system was set up. Did not include Earth. So did I do that? Sure. In fact, it was in the second block where I primarily discussed energy. So let's see here. It does negative work. Okay, so the force of gravity does negative work since it blah, 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 reduces the kinetic energy. Okay, so basically strung in there, I have included everything needed to satisfy that point. Moving on. Let's try a pink highlighter. 1 point for a correct statement that the ball compresses. Okay, so this is taking to that greater depth of understanding that this rubber ball is not as idealized as we often assume it to be. So it compresses when it hits the wall, converting some kinetic energy into internal energy. So that that momentarily compressed ball stores energy in that deformed shape. Kind of like an elastic band, if you will. If you stretch out a rubber band, because it is rubber and therefore elastic, when you stretch it, it stores energy. Or also more akin to like a spring, if you've come across that. A spring that is stretched or compressed similarly stores, quote, internal energy, which sometimes goes by other names like spring energy or spring potential energy, but in that context it'd be the same thing. Okay, so it converts some of that energy back into kinetic energy as it leaves the wall. So I've got that when I discuss the collision in detail here. So approaches upon impact, some of the kinetic energy is transformed into internal energy, etc., etc., etc. And then, of course, some of the internal energy is transformed back into kinetic energy as it rebounds from the wall. So everything that you see there, approximately, would satisfy that point. Okay, moving on. 1 point. For a statement that the ball is going faster vertically when it hits the ground because it is lower than when it was thrown. So this is that point that I think I would have missed if I had just attempted this question on my own without looking at the points. It just didn't occur to me to include this. And there's a little detail here that I don't think I need to explain here. The full credit was given even if you missed something. Okay, that's fine. So the point is that because it is even lower, then the vertical component is greater, or at least the magnitude is greater. So I made sure to include that. Okay, so in fact I gave a little bit extra information here that is relevant, so it's okay. So yeah, okay, magnitude balls vertical velocity 0. It will be back to its initial value, and I'm discussing the vertical component of velocity. It'll have the magnitude, okay, just again to stress that, the magnitude will be equal when it passes that same height that it was thrown from. Okay, so that alone does not get me the point. It's not until I go one step beyond that to say it then increases to even larger magnitudes as it moves to lower heights. In fact, being a maximum when it strikes the ground. So not all of that was exactly needed here, but nonetheless, that's where I would earn that point. Okay, so we're 6 points in. The 7th point is not a point that I'm even going to highlight. It's more of kind of like a kind of a big picture point. Okay, you have to like zoom all the way out and kind of look at this whole answer that I provided. So this point, this last point, well, I said I wouldn't highlight it, but let me just emphasize certain things within it. So your answer has to be logical. It has to have a internally consistent argument. It has to have relevance. It basically has to be a, quote, good answer in the opinion of an expert in the area who is grading your paper. So this is arguably a little bit subjective, and that's fine. But basically, imagine the person who's grading your paper, imagine that they have just finished reading your answer. They ultimately are going to form a subjective opinion of saying, okay, I have just read this student's answer from beginning to end one time. Okay, it's not like I had to go like, wait, what? They didn't throw me. I've read it through one time, and yes, this student really gets it. The answer was correct. It was logically laid out. It didn't like confuse me in any way. You know, I'm an expert in this field. I'm the person grading your paper. So you didn't say anything that kind of like made me say, wait, what? So in any case, there is that subject element to it, and I'm going to claim that I feel confident that I would have earned that point here. It was logical, it was relevant, etc., etc., etc. So it basically satisfied the standard requirements for a paragraph length answer from the AP guidelines, which I should mention also include things like it didn't include a whole lot of irrelevant information. It didn't have any incorrect statements. So yeah, I'm pretty good for that point. So this really would be, I fully expect this would earn all of 7 points on this part of the question, as well as the previous points. So this should get all of the points. So hopefully that was of some help to you. Like I said, there are 5 questions in total that were released from BFW. This is the second of those 5 questions that I have planned to, because I haven't done the others yet. This is the second of the 5 that I'm hoping to make solutions for. So stay tuned for the remaining 3 coming up soon as I'm able to do so.